Today's presentation is on gas stoichiometry, section 14.4 in your books. Recall regular stoichiometry that we had before, going from mass to moles, moles to mass mass, using the mole ratio, using the coefficients from the balanced chemical equation. It's the only time we use those coefficients. So here we have our balanced chemical equation. We have carbon monoxide reacting with oxygen to form carbon dioxide. Remember the coefficients in front of the numbers. 2 can represent 2 moles, reacting with 1 mole of oxygen to give us 2 moles of carbon dioxide. When we do the gas laws, when we work with the gases, we can do the same thing but with volumes. Volumes meaning milliliters or liters typically is what we'll have. This also tells us that we have 2 volumes of carbon monoxide reacting with 1 volume of oxygen to give us 2 volumes of carbon dioxide. Again, we can use liters or milliliters, whatever the problem is written in. So the volume ratio of carbon dioxide to oxygen would be 2 volumes of carbon dioxide over 1 volume of oxygen. Let's do an example. What is the volume of nitrogen gas? What volume of nitrogen gas is needed to react completely with 150 milliliters of hydrogen in the production of ammonia? So here we have our balanced chemical equation. We're looking for the volume of nitrogen. We are given a volume, 150 milliliters, of hydrogen. So here we have a problem. One way to identify a stoichiometry problem from any other type of problem is that you will have a balanced chemical equation for one. The other ones will not. And also, we're going to be talking about a couple of different things. We're going to be talking about a couple of reactants or products. Here we're talking about nitrogen and hydrogen. So if you talk about a couple of different things, then it's going to be a stoichiometry problem. So if we're just looking from volume to volume, in this case, we just have to do the volume ratio, in which we start out with what we're given. We are given 150 milliliters of hydrogen. So that's what we start out with. Put our liters of hydrogen, or milliliters of hydrogen in the denominator, our units. We're looking for milliliters of nitrogen, so that goes in the numerator. And then we look at our balanced chemical equation. For nitrogen, we have a 1 here, so that goes a 1 there. For hydrogen, we have a 3 here, so that goes down there. Milliliters of hydrogen will cancel, the units will, so we will end up with 150 times 1 divided by 3, and we'll get our answer of 50 milliliters of nitrogen. Simple as that, just a standard mole ratio. But again, with gases, we can do that with volumes. If you have a problem dealing with volumes and mass, then you have to use your regular stoichiometry and do the 3-step process. These are problems dealing with grams to liters and liters to grams. We just use one of the other legs of the stoichiometry island that you have. So you'll want to have that out for this section, so to follow along. Also to work out these problems. Might be a good idea to have that out. Let's take a look at your packet, page 15. What mass of nitrogen is needed to react completely with 150 liters of hydrogen in the production of ammonia? Again, we need our balanced chemical equation, which we have right here. And now we need to start plugging in numbers. Start with what we're given. 150.0 liters of hydrogen. So that's what we're given. Parentheses line, liters of hydrogen in the denominator. If we look at our stoichiometry island, first thing we need to do is go from volume to moles. We do that by putting in our units in the top here, moles. And then we can look at the numbers that we need to put in here. We need 1 mole, and that will equal 22.4 liters. That is what the volume of 1 mole is, 22.4 liters. So we put that in there. Next one, we need to do, actually this is moles of H2. Mole of H2 in the denominator. This is going to be our mole ratio now, going from mole to mole. Mole of what we're looking for. We're looking for nitrogen gas, so we're going to go with moles of N2. Now we're looking at the coefficients from the balanced chemical equation with this mole ratio. So for H2, we have 3 in the denominator. For N, nitrogen, we just have a 1 there. So we'll put a 1 there. And our last setup, mole of N2 goes in the denominator. We are looking for grams of N2. By definition, 1 mole of N2 is equal to the molar mass of N2. Remember, this is N2, so we have to take the molar mass of nitrogen, which is 14.0, and multiply it by 2. So we'll get 28.0 as the molar mass for our nitrogen. Now our units will cancel out. Liters of H2, liters of H2. Mole of H2, mole of H2. Mole of N2, mole of N2. We are left with grams of N2. So now we need to do our multiplication just like in the past. 150 times 1 times 1 times 28.0 divided by 22.4 divided by 3 divided by 1. And we'll get our answer of 62.5. And that will be our answer in grams of N2. Again, just like the other stoichiometry problems, but now we throw in our volume, which is going to be an easy calculation because whenever you have that volume, the volume of a liter is 22.4, or the volume of a mole is 22.4 liters. That's all we have in your packets. Page 14. Problems 1 through 3 are due. 4 and 5 are extra credit. Page 15, 1 through 3 are also due, and 4 is extra credit. So not a lot of problems. We're getting down to the end here. Last sections, not a lot of problems to work out. Just a couple of them there. And then there's some extra credit. Do this work. Get the extra credit. Not that hard to work 1 or 2 problems to get those extra points. Very easy to do that. And that concludes our presentation.